So my work is I'm working with Professor Bhaskar Rao. My name is Rohan Pote. I'm a third year PhD student and started working with Professor Rao since last year. So um, in a contrast to what the previous talks have been, either they combine machine learning. Uh, Basically, my talk doesn't have any machine learning or those aspects, but it's more theoretical. But it tries to solve some of the problems that uh, the previous talks tried to address. In particular, we are trying to reduce the training overhead for the channel estimation. What we do here is we use sparse arrays, and basically we are trying to uh, link some of the array processing literature to the millimeter wave channel estimation uh, problem. So the overview of the talk is I'll first discuss the motivation behind using this geometry for channel estimation, and a couple of geometries I would discuss, the conventional uniform linear array, and one of the sparse arrays called nested array, and I'll talk about a couple of techniques how we can incorporate these geometries in the system, and finally I will summarize my talk and lay down some future work. So as we all might know that millimeter wave channel is sparse, so there are few number of multipaths, and the channel estimation problem boils down to doing angle estimation and path gain estimation. Also, the millimeter wave architecture has this constraint that the wavelength is small, we pack many more antennas in the same surface area, but the number of RF chains doesn't grow with it. And it would be nice if we could capture the essence of a larger aperture with merely selecting a few of those antenna elements and connecting it to the RF chains directly. So before going into the details, let's just first discuss some of the geometries of antenna arrays. This is a uniform linear array. Here, as you might know, the aperture is linear, and we place the antenna elements with a uniform spacing d. And this is the sensor positions, how the sensors would be placed, and the maximum lag is a quantity that is very important for doing direction of arrival estimation, let's say. The maximum lag is basically the distance between the first and the last sensor of the array. And the larger the aperture, it gives us more resolution in the direction of arrival estimation. This is one kind of a sparse array called nested array. Here we have two subarrays, and both the subarrays are uniform linear arrays. The inter-element spacing between two elements in the subarray 2 is a function of number of elements in the first subarray. So basically what we are trying to do is, using the same number of elements as in a uniform array, we are trying to increase the aperture by allowing some holes to be there in the array. And by increasing the aperture, we get a more fine estimate of the angle of arrival. To put things into perspective, here this lag, this important quantity, was of the same order as the number of elements that we used. With the same number of elements, the lag is of order n square. So this has important consequences as to on how better a DO estimation problem can be solved. The key takeaway from the slide is nested array has a greater aperture and a large lag set. So a couple of simulations to show how nested arrays can do the same problem more better. Here I have, let's say, an antenna array with 12 sensors, and 25 signals are impinging on the array. And with a uniform linear array, you cannot simply solve this problem. You cannot estimate 25 direction of arrivals with 12 sensors. But with a nested array, you can do that. So in this ring, basically the dashed lines are the true ground truth angle of arrivals, and these points are basically the estimates of the simulation. And basically the point here is that nested array can solve this problem where uniform linear array cannot do it. Even in cases where both the array structures can solve the problem, we should still use nested arrays because it is more robust to sensing. So here, as you can see, this plot is for uniform linear array, and the cloud is it has a much more variance of estimation. So its estimates are poor as compared to what you can do with nested array. and it also can be seen theoretically using Kramer-Rao bound. Basically, the variance of estimation, it goes down as n raised to minus 5 for nested arrays. For ULA, it goes as n raised to minus 3. So both theoretical and simulation performance are superior when we use nested arrays. So to wrap up the introduction part, we know mmWave have these two characteristics that basically we're trying to solve a DO estimation problem, and it would be nice if we could use arrays which can solve that core problem more better. And there are a couple of techniques we have for this. One is pure antenna selection, and second is doing this beam space design in a reduced dimension. Reduced dimension because we have lesser RF chains as compared to the number of antennas. So the antenna selection problem is pretty simple. Whatever architecture, whatever sparse array we wish to create, we can merely select those sensors in the large aperture, and we would have our sparse array. So here we ask this question that let's say we have a large ULA of size n, and we were to basically construct a sparse array such that the aperture is same as the full size ULA, and we would need only order root and antenna elements to be sampled. So to put things into perspective, let's say we have 64 element ULA aperture, and the question is how many RF chains do we need to have the same aperture as, or some of the same properties as this full ULA, and we need only 15 RF chains. So this thing grows as order root n, where n is the number of antennas. It's also known that pure antenna selection is generally not enough in the channel estimation phase, because you don't know where the users are, and the mmWave channel it has a large propagation loss. So we need some beamforming gain, and pure antenna selection doesn't give that. So in order to get this beamforming gain, we would have this next technique. Basically, in literature, what we try and do is we get this beamforming gain by combining all the antennas and basically doing a spatial search. And this is basically trying to solve a detection problem. You look into binary regions, okay, is the user here, is the user here, and then you narrow down and have a final resolution of an estimate. But it's a coarse estimate, because if you want to do a very fine estimate, the training overhead is just too large. And what we would like to do is we would like to do a DOA estimation instead of this detection. And basically, this is the point of this next technique. So basically, in the antenna selection, we missed the beamforming gain, and this is what we would like to construct in this technique. So here, in this construction, what we have is these are the real antenna elements. So these are the actual antenna elements that are placed in the array, and we construct these virtual antenna elements by combining a few of these real antenna elements. And the construction, basically what it does, it combines a subset of these antenna elements to construct one antenna element. And this construction continues in the same way. Basically, we combine linearly a few of these antenna elements, and depending upon how these weights are chosen, we get some beamforming gain. It's basically trying to mimic a linear time invariant system, and since these array manifolds are complex exponentials and which are eigenfunctions to this LTI system, basically what we are trying to do here is, although we have constructed these virtual antenna elements, they should still represent in some manner what real antenna elements look like. And this construction, using this mimicking of LTI technique, basically it ensures that these still look like some antenna elements in a virtual space. And depending upon how we choose these weights, you will get some beamforming gain. And these are basically from the filter design aspect. So in the next slide, basically I would have I would discuss how much the beamforming gain you can get, and whether these virtual antenna elements do they represent some form of real antenna elements. And so here in this picture, one can see that depending upon where you want to zoom in the spatial region, you would choose these filter coefficients, and you would get this beamforming gain. For example, if you're interested in these angles in the spatial domain, we can get this beamforming gain, and the reconstruction of this array manifold is exact because of this mimicking of LTI system technique. So what we would like to do with this kind of architecture is we would like to zoom in narrow regions, and would try to have or use some direction of arrival estimation literature to do super resolution estimates of direction of arrival. So basically, for example, if you want to track mobility in a coarser area, which some of the previous techniques can do for us, within that coarser area, if we want a super resolution estimate, we can use some of these techniques to get that, and tracking mobility. So basically, we have the training overhead is not linked with the channel estimation if you use some of this technique. So to wrap up, we know that nested arrays can solve this underlying DO estimation problem better than uniform linear arrays. And we also know that nested arrays can play some role in millimeter wave channel estimation because they need fewer RF chains to cover the full aperture. And we saw a couple of techniques to incorporate geometry, and the channel estimation, the precise algorithm is still to be looked into, but these two techniques we have already published it for Asilomar, which happened recently. And thank you. If you have some questions.
Thanks, Rohan. Question from Charlie.
Okay. Thanks, Rohan. So if you go back one slide, the beam looks pretty wide in this picture here.
Yeah.
So is this by design?
Yeah, so this was just an example to show what it can do. So basically, how narrow a region should be. It is designed by how you choose these filter coefficients. It's a filter design problem.
So how do I understand this? So now you have reduced degree of freedom. Mm-hmm. Can you still design the beam as you wish, either to be wide or narrow, similar to the size of virtual array, right? In this case, your virtual array size is 64, mm-hmm. whereas you are using 15 RF chains to mimic that, right? Mm-hmm. Do you get the same type of design flexibility, scanning range, and in the traditional array, if I have 64, right, I can control it.
Yeah. So basically, as you can see, we are not using all of the antenna elements to construct one virtual element. So the beam width that we can hope to get this particular, if I call this as the beam width here, we cannot hope it to be as good as combining all of the antenna elements. But the thing is, that is the main purpose. We don't need to zoom into very narrow regions. As soon as this beam forming gain is good enough so that we can sense the signals at least. Now on top of it, we are trying to do an estimation problem. We don't have to say that we don't have to have a very narrow beam to say whether the signal is present or not. We'll just estimate them.
I understand. I mean, there's different applications. I mean, for the sensing purpose, mm-hmm. More of a continuation of radar, but I'm more thinking for communication purpose.
Yeah, so basically this entire design is trying to do channel estimation, and once we have a very good estimate of the channel, then we'll have to go back to the conventional techniques where we combine all of the antenna elements to zoom into that particular user to get the beamforming gain and the SNR boost and stuff. But this is more to do a better channel estimation. Once we know the channel, when we have tracked the user mobility properly, we can go back to using hybrid architectures and do data transmission.
Yeah, thank you. Yeah.